So, okay, let me just get started. How many of you know what a xWAS is? Perfect. Yeah, I knew you would know that. Okay, so you know that we discovered hundreds of thousands of loci, but we don't know what they do, mostly, right? So which is very frustrating. And, 10 years ago now, more than 10 years ago, we proposed this method that we call PredictScan in order to try to explain, at least from the locus, what's the gene, right? So even today, we still don't know. So we proposed this method. So xWAS, I'm going to go over this so you will remember the notation, because today is Statistical Genetics 101. So you will get a free StatGen course. Okay, so we have our genotype data. It's this matrix of where rows are people, columns are SNPs. I'm just going to call them SNPs. Could be other genetic variants. And then we have the trait. It's a vector of Y. We call them Y. Same number of people as in this matrix. And then what do you do in a xWAS? You already know, but it's just the simplest thing you could ever think of doing with this data, which is run a linear regression of your Y on each one of these columns, one at a time. That gives you this table of xWAS results. Rows are SNPs now, and columns. So I like to call this delta. So I'm trying to sort of, impose this notation, because when you read statistical genetics paper, it's very hard. Everybody has a different notation, and you think, what is delta, alpha, gamma, epsilon, and all that? Epsilon, we should call epsilon is noise, right? Let's not call epsilon something else. And don't use J for people, use I for people, please. So delta. So we have many effects: SNP to phenotype, SNP to gene expression, SNP to protein levels, and so on. So delta, I reserve it for SNP to phenotype, because it's disease, right? Delta disease. So I told this kind of a joke, but not completely. So if you use this notation, it's more likely that I will accept reviewing your paper. Okay. So then, because we don't know what these SNPs do, we kind of, we could run this transcriptome-wide association study where you take observed expression levels and do the same thing, right? Y against each one of these observed expression, and then that would give you this gene level results. And these effect sizes, now I call them beta, right? Because that's the effect size that we are, at least in this context, we're most interested in. Okay, so what are some of the problems with that? You already know RNA sequencing is very expensive. There are many tissues like brain, pancreas. You can't really access them, so you can't just measure this at the same scale as you could do xWASs. And another thing that's important is that observed expression levels can be affected by the disease. So if you find genes that are differentially expressed, that doesn't mean that those are causal. They could be reverse causality. So then we proposed TWAS or PredictScan, where you take the genotype data and you extract the genetic component of that. And that genetic component is a function of your germline genotype, so it doesn't get changed by whether you have a disease or not. So you do the same thing. Instead of using observed transcriptome, you do predicted transcriptome, but this transcriptome is the genetic component. And you do the same thing, you end up with gene level results. And you predict this. In order to do this, you need reference data sets where you have gene expression data, like in GTEx, where you have gene expression in many different tissues. Same genotype data for the same individuals. You fit this linear model, you're good to go. Okay, how well, can we even predict this gene expression? I always find it useful to see how well we can do this. And these are cherry-picked genes. So these are the genes that, with this method, correlate best with the observed expression levels, right? You see very high correlation. That's good, but in general, if you look at all the genes that you try to predict, so their heritability are shown here, so ordered by heritability values, and then in red are how well you do. So genes that have expressions that are more heritable, the points are higher, so we predict better. Genes that are not, that have expression that are not heritable, that don't depend in principle of genotype, we don't do well. So this is one tissue gene whole blood.
Okay, whole blood. Yeah.
Whole blood, yeah.
Okay.
Yeah.
Red dots are
R squares, R squares.
And is that something variants why they can exceed heritability sometimes?
Because this is all noisy, right? Yeah. So R squares are estimated, heritabilities are estimated. So that's why we get that, yeah. Okay, thank you. Very good asking questions because you're prepared for the quiz at the end. So I'm not going to go over the advantages and disadvantages. So some, people have used this idea, predicted expression levels to identify drug repositioning candidates. We have shown that it's sort of PredictScan or gene level results are predictive of the success of drugs in the drug development pipeline. But TWAS have many limitations, but that's not the focus. So that was just an introduction to get familiarized with the notation and also to impose a standardized notation that is easier to read. So, okay, the idea of TWAS is take the genotype, predict expression levels, and correlate with the disease or your phenotype in order to identify what's the causal gene. But you could do this the same with the epigenome, alternative splicing, metabolites, and so on, right? And people are developing methods, and even last year, this kind of, CGSI, xWAS was published last year or the year prior. IsoTWAS, I think it came out last year, or even this year, I don't know. So this is an active area of research, right? So do you know what a FWAS is? We have the person who ran the first FWAS, right? Can we say the pioneer of FWAS here, Lisa Bastarash, if you didn't know?
Yeah, it's a phenotype-wide association study.
Yeah.
Nobody else has done it? Oh yeah, told you about it yesterday.
Yes. Okay, so people are running FWAS instead of the SNPs, of PRS. So you take the genotype data, calculate the PRS, right, which is a linear combination of the genotype that's correlated with your disease. And so instead of running FWAS at the SNP level, they're running FWAS with the PRS. So that would give you this kind of interesting results where you have, I think this is depression, right? Depression is associated with depression, that's good, that's an excellent positive control. But then you have all these kind of less significant but interesting things that have to do with white matter microstructure, and you could start, so this gives you a lot of information about the biology, maybe it informs your pathways and so on. So this is one of the ways in which PRS are using for the skeptics. Probably the skeptics are not here, but anyways. Okay, so I'm motivating where I am going, right? This is another FWAS, and they find Tourette syndrome associated with anxiety disorder. When it's this close to significance, I start becoming a little bit more skeptical. Back pain, Tourette syndrome, I don't know. You can start making up stories, but yeah. HbA1c, does Tourette syndrome have to do something with diabetes? I don't know. So, but the thing is, this is another paper, I was a co-author, where they take PRS of asthma, and then you find all these hugely significant things because you run it in the UK Biobank, right? You go to the UK Biobank, take the genotype data, calculate the PRS, in this case of asthma risk, and it's associated with all this leg fat. Yeah, COPD, like the very extreme one, the asthma, the PRS of asthma associated with asthma, that's good. COPD, they have comorbidities. You could think that they share.
Haky, the triangle's upper risk and lower is
yeah, I think so. Yeah. So FEV, yeah, makes sense. FEV is lung function. So if you have asthma, you have less lower function. Okay. Sorry?
No height.
What was the question?
He's looking for height on there.
Height. Here.
Oh, we got it. Oh, yeah.
Right there.
I thought you said no.
Yeah, it is right there. Yeah.
Huh.
Good. So Okay, so people are using it, right? It's out there. So when this report came out, it was worrisome. So Liu et al. Said that TWAS, and TWAS mean any linear combination of SNPs associated with your phenotype will have the same issue, right? TWAS yields inflated type 1 error. So they published this paper. When the preprint came out, they said on the validity of TWAS. And in the paper, they would say if TWAS is invalid because of this, right? So after rounds of reviews, ended up saying on the interpretability. Okay, so there are known sources of inflation which have to do with this, but this is not referring to this. So that you know, right? If you have two SNPs, one is affecting your expressional level of the gene, and the other one is the causal SNP for the disease, then if they are in LD, TWAS will give you association, right? That's LD contamination or LD confounding, depending on who your PI is. So the other thing is that if a SNP affects expression levels of two genes, but only one of them is causal for the disease, then you will still find this thing, right? These are confounding that we know exist. It's like when you run a GWAS, you have a bunch of SNPs. You know that they are all they're not all causal, right? You get this cluster of confounded, LD confounded SNPs, and in this case it's even worse because in addition to LD, you have this co-regulation thing. But at least this TWAS will give you a kind of a smaller list, right? A prioritized list of genes. So this is something we know, and then the field still considers that this is useful to do. But what they are referring to is something more fundamental and more serious. So your p-values are wrong. That's what. If your p-values are wrong, you cannot call anything significant or has no meaning. So the model is like this. You see I'm using beta is the effect of the gene, predicted gene, or the genetic component of the gene, and then there's the error. So this gene expression level is represented as this linear combination of SNPs. So X sub Ks are SNPs. Gamma, so gamma is effect of SNP to gene, gamma gene. So, okay. So what they are saying is that because your prediction is noisy, because we don't know the exact prediction, right? That noisiness, that noise makes your type 1 error completely messed up. You cannot use this. So that's what they claim. But if this error is independent of the gene expression, the true gene expression level, we know there's a whole theory, a whole field of error in variable field that tells you that this does not cause inflation in type 1 error. Your p-values will be fine. The only thing is if there is a true effect, you will have lower power. So it reduces the power, it doesn't increase the type 1 error. So this doesn't make a lot of sense, what they are saying. So if you look at I changed a little bit the way I present this because I don't want to be presenting this and then have lows in front of the audience. So, okay. So, yeah. So if you read the paper, they say, okay, so the null hypothesis testing 101 is that the beta, the effect, is equal to 0, right? That's a typical null hypothesis. But they say because TWAS uses the noisy version, the null hypothesis is actually this thing here, where the beta hat is not the true beta that is 0, it's the estimate of the beta. So the estimate of the beta is what statisticians call a statistic. And does anybody know what statistic means for statisticians? It's a function of the data. It's a function of the data, it's random, right? So this beta hat is a random variable, continuous random variable. So what's the probability that the continuous random variable will be exactly 0? 0, right? So it doesn't make sense. You cannot, you just don't do hypothesis testing like this, right? So, and then they keep doing that, and finally they prove that because this is the null hypothesis, then you get inflation. I mean, the paper is hard to follow because they are kind of trying to be statisticians but not being completely rigorous. So anyways, so, but you know, there was something there, so we decided to investigate. So the way I learn is by doing, right? So and using simulation is great because simulations, you know the truth. So we have y, which is beta t plus epsilon, the error, and then t is just a linear combination of SNPs, right? Where epsilon and this is the t are independent. That's linear regression assumptions. If you don't believe it, then you don't do linear regression, right? So those are kind of you have to be ready to accept those assumptions. Otherwise, you have to do something else. So this is a very simple simulation, right? So beta is equal to 0. That means null hypothesis. When you calculate type 1 error, and this is something that even, you know, experienced statisticians get confused because we have our, you know, statistics is not intuitive. That's my point. So, okay, but if you know, kind of stick to the actual definitions, you will get the right results. So beta is equal to 0. That means we are working under the null hypothesis. Here, to make it kind of computable within reasonable time, it's a sample size of 1,000. M is the number of SNPs. So I like to have different numbers for N and M so that, you know, that will catch any errors I have in the coding. Minor allele frequency 0.4, just because. Epsilon, the error, is just normally distributed. Gamma, in this case, I'm just getting the error, the gamma, the effect sizes from the normal distribution. I'll show you something else later. And then X is the genotype. So use binomial distribution with this will give me a matrix with n people, m SNPs, right? So that's
does it make a difference that you assume all the allele frequencies are 0.4?
That I am assuming that.
Yeah, well,
does it make a, yeah.
I mean, in a real life example, there'd be variable.
Yeah.
But that doesn't, it's not going to matter.
I'll get there.
Okay, sorry.
Yeah. This is the simplest thing you could do,
Okay,
right?
Yeah,
just,
fix
yeah.
everything. Okay.
But yeah, those are all and the nice thing about having these few parameters is that, where could the issue be, right? And then you can change this. We could have a mixture of minor allele frequencies and so on. So all of this is what we wrote there, and y is just beta t, but remember beta was 0, so this is not contributing, it's just a normal random variable. So then you fit y on t, that's the TWAS, right? And so you can do that. And then so the chi-square statistic is, so that when you run linear regression, that will give you, the output will give you effect size, estimated effect size, and the standard error. So if you take the ratio, what's that called? I'm testing you. Estimated, what do we call that? Beta hat over standard error of beta hat. What's the distribution, asymptotic distribution of beta hat? Estimated, right?
Standard normal.
Standard normal, good job. Stickers for you. So, asymptotically standard normal. So you take that, you square it, that gives you chi-square. So that's the chi-square statistic. That I am going to talk about chi-square statistics, so that's, I'm reminding you. So when you do this simulation, you run this regression, you get, and then you can calculate the chi-square statistic, right? You do it 1,000 times, and then every point here is one simulation. And then you can compare the points, the chi-square statistic, as a function of what you would expect. The expected is standard chi-square with 1 degree of freedom, and this is the observed. You know, kind of seems to be in the one-to-one line, so that's promising. And then the sample mean, so if we take all these points and calculate the average, I get 0.94, which is not exactly 1, but it's close enough. And then, you know, this is the gray bars show you what you would expect if you, just by chance, right? What the normal variation you would expect if you take actual standard chi-square with 1 degree of freedom 1,000 times and you take the sample mean. So this says that if the error is independent of your predicted expression, then you're good, right? This is all good. So when the mean chi-square is 1, we're going to say this is not a problem, right? It's not inflated. If it's greater than 1, we're going to say that the test is inflated. So now we're going to add a polygenic component. So y, the epsilon, right? We know that it's not all determined by the expression of the gene, right? In fact, we're under the null hypothesis, so beta is even 0. So the epsilon TWAS, it has a polygenic component plus epsilon, right? So most traits that we're looking at are polygenic. So this is kind of an accepted thing. And if you've ever used LD score regression to calculate heritability, that's the underlying assumption. If you don't assume that, then LD score fails miserably. So most diseases, complex traits are polygenic, so we recognize that fact and we add that. So then we do the same thing. We simulate the same idea. So we have delta, the effect on the polygenic effect on the phenotype. Everything is the same. Yeah, everything is the same except for the fact that the epsilon, the error that we add, y has this polygenic component. So this matrix multiplication will give you the right thing, right? This will be x times delta. So it will give you that thing there, sum over k of xk delta k. So what do you think will happen? So keep in mind that t here, right, your kind of explanatory variable, is independent of epsilon because the deltas and the gammas, by how we are simulating, they're independent, right? So the assumption of linear regression where t is independent of epsilon still remains in effect. So what do you think will happen if we calculate the chi-square statistic? Will we get inflation or no? Yes or no? Just guess. It doesn't matter. Right? No inflation, right? There's no reason we should get inflation because this the assumption of linear regression holds, right? The t that you have is independent of epsilon. It's independent in a weird way. Yeah. We were surprised. We didn't expect this to happen. So this should be here, is there. The mean expected chi-square should be here, somewhere here. It's way over. And the cause of this is the polygenicity of y, not the error in the prediction as the other paper was saying. Okay, so sure, no, we have to deal with this. Yeah.
Quick question. So for the xk here, so are the same set of SNPs? So the k index are.
They are all the SNPs. Yeah, the same set of SNPs, right? Yeah.
Okay.
Mm-hmm. Yeah. Yeah.
So those SNPs are directly influenced on y, but not through genes expression.
Yeah. So sort of the expected value of epsilon t was times t will give you 0. They are independent.
Okay.
But for some reason, we have this inflation. Like?
I was just wondering, I know you say that statistics are not intuitive, and I agree with that.
Yeah.
Here is the intuition would be like a mixed model kind of situation where you have covariance essentially by creating that, you create non-independence between people.
Yeah. 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 The way I like to think about it is that we're all related ancestrally. I don't know if it's the right explanation, but yeah, it's relatedness will give exactly the same effect. So this thing here is relatedness, right? So yeah, that's great. Okay, so what do we do with this? Okay, that was simulation, right? But that was the simplest possible simulation where you wouldn't expect inflation and you do see inflation. So here is using UK Biobank data. So you take UK Biobank data and you take actual expression prediction of, I don't have the name here. This is one gene in particular. So, and then you predict the gene expression, and then you correlate with the null phenotype in the UK Biobank. So there is no such thing as null phenotype in the UK Biobank because, watching TV has a lot of GWAS hits. Everything has, nothing is null. So what we did is we took the genotype and just simulated null phenotype as a polygenic null phenotype. But this is a real data case, right? If you take a polygenic trait that is random, because you just generate the weights at random, and you correlate with predicted gene expression, and then you calculate this is chi-square, right? The observed chi-square versus expected chi-square under, the normal assumption that there is no inflation, you get this thing, right? So you will get. So the point is, yeah, you do see exactly the same thing when you use real data.
And the
With
random trait was like a genotype from some other part of the genome or something like that?
No. That's so our assumption is full polygenicity. Every SNP has an effect.
Yeah.
So it's just we randomly generate effects from the normal distribution and multiply genotype by that random effect and sum over genotype. So it's sort of PRS, random PRS. PRS. No. Anyways, yeah. Okay, so so is it a problem? Yes. You think the blue is the standard chi-square, and then the red is the non-central chi-square that we're finding. And if you use the wrong distribution, then you're going to think that p-value is this tiny area under the curve here, but in reality it's much bigger, right? That's the problem of using this wrong distribution. I mean, I probably don't need to say this in this, but Okay, so we looked at the properties of, I think I don't have a lot of time left. So this is again UK Biobank data, actual gene expression, the gene is there listed. And then, so if you calculate the average chi-square, that should be 1. We believed all this time we were working under the assumption that it was 1. It increases with the heritability, increases with sample size, and in fact, if you multiply sample size by heritability, increases linearly. So instead of being 1, it's kind of, So with biobank scale data, it's going to get worse and worse, right? Because it just keeps going up. So based on that, that behavior, we can sort of hypothesize that the expected chi-square will be 1 plus n times h squared plus the slope of that thing, right? So we do the math, and you get actually this formula where C over M would be the equivalent of phi. And yeah, that's the formula. So so we see both empirically and theoretically that there is inflation if your Y is polygenic, and as Loic mentioned, you can think of it as the polygenic component is the relatedness. Well, can we estimate the inflation factor? Yes, you just estimate the slope, right? Given that formula. So if for those of you who remember the LD score regression formula, you will see that it has the same functional form. Anyways, so you can you get the same thing for gene expression, metabolites, brain features. You can estimate that slope, and this is what we find. And something that's interesting, brain features that are very polygenic, they tend to be more concentrated in this number. For metabolites, it's a little bit more spread out, and for gene expression, even more spread out. So how do we correct for this inflation? Use the right distribution instead of the wrong, so the red instead of the blue, although no political implications of that. I should flip that to reflect my own. Anyways, okay, so how do we correct for inflation? So under this, we can estimate the non-centrality parameter phi. That phi is the slope of that thing that I showed you. And then you use the non-central chi-square, which in R would be this formula here. That's it. So Okay, I'm not going to go over all this and go to the take-home messages. Yeah, sorry. So standard TWAS or xWAS or PRS-FWAS, anything where you correlate predicted thing, linear combination of SNPs with your phenotype will have this problem. And I keep saying this because one of the reviewers said that this was a problem with PredictScan, which I don't know how you could conclude that. Anyways, so that will yield inflated p-values, and even without considering all the known issues of TWAS. So the chi-square statistic you get is non-central, but the non-centrality parameter can be estimated. And also this slope is a function of the gene or the feature rather than the phenotype. So you can estimate, pre-compute it, and that's what we are doing, and share it with our users so that they can correct the inflation. Okay, I will stop here.